I am Alessandro Ronca. I will present Temporal Logic Monitoring Rewards by Transducers, which is a joint work with Giuseppe de Giacomo, Marco Favorito, Luca Iocchi, and Fabio Patrizi. We have studied the problem of rewarding an agent for its behavior over time. To give you a concrete example, consider the case of a mail delivery agent. This agent has to deliver mail from a post office located on one side of a lake to a town located on the opposite side. The agent is able to go through the lake, but if he does so while carrying mail, the mail gets wet. So it would be better if he goes around the lake. For this reason, we may consider to give the following rewards. A positive reward when the agent delivers the mail without going through the lake. A negative reward when the mail gets wet, so when the agent goes through the lake while carrying the mail. And a small negative reward at an instant before the delivery, so that the agent tries to deliver the mail as quick as possible. The important thing to notice is that each reward condition refers to an extended period of time. And I will present monitoring rewards, which are our main contributions. And I will show that all these three rewards can be captured by one monitoring reward. Particular monitoring rewards improve on existing temporal logic specifications for reward, allowing better control over reward assignment at no additional cost. In the paper, we also argue that reward transducers are a more convenient formalism than reward acceptors when we are not interested in the source of the reward. I will first introduce the necessary background. The problem we study can be formalized using decision processes with non-Markovian rewards, where one of these decision processes consists of a finite set of states, a finite set of actions, a Markovian transition function, and a non-Markovian reward function. So by non-Markovian, I mean that the reward function assigns a reward looking at the entire trace generated by the agent interacting with the environment. So the sequence of states and actions generated so far. That also means that if we take another trace that is almost identical to the previous one, except for the fact that S2 has been replaced by S prime, now this trace may be mapped to a different reward, R prime, even if the last elements are the same. The formalism that we extend is the formalism of temporal logic specifications of non-Markovian rewards, where one of these specifications consists of a reward condition expressed in linear temporal logic on finite traces or linear dynamic logic on finite traces, and a real number. The way it works is that we look at the trace generated so far, and we check whether the condition is satisfied over the trace. If it is satisfied, we issue the reward. The good thing about this formalism, and in particular about decision processes with non-Markovian rewards expressed as temporal logic specifications, it can be compiled into Markov decision processes. This can be done by first computing the deterministic finite automaton for the reward condition, and then computing an extended state space that includes the states of the original decision process together with and a component coming from the state of the deterministic automaton, and then also defining a new transition function and reward function, now Markovian over this extended state space. Now we'll introduce monitoring rewards, which are our main contribution. The idea, as I said, is to extend temporal logic specifications. Looking at temporal logic specifications, we thought it would be nice to still have the reward condition, but now to assign different values based on how this reward condition is satisfied. Particularly, we thought that, okay, we still have the reward condition still expressed in LTLF or LDLF, but now we want to have 4 values, which get assigned in different occasions. In particular, we took the idea of the 4 classical monitoring conditions and we built on it. So now we don't look at whether the formula is simply true or false in the current trace, but we look at whether the formula is temporarily true or permanently true, temporarily false or permanently false, where we say that the formula is temporarily true if it is true, but can still be false in an extension of the current trace. And for instance, we say that it's permanently true if this cannot happen. So it is true and will always be true. Now we look at the current trace and we check whether the formula is, for instance, temporally true in this trace. If it is temporally true, we assign R. But if instead is, I don't know, permanently true, then we assign S instead. Going back to the initial example of the mail delivery agent, the task of this agent can be captured by this one monitoring reward, where the reward condition is not lake until delivery. So the agent shouldn't go through the lake until it gets, before getting to the delivery point. What happens here specifically, this formula can be temporarily false, permanently true, and permanently false. However, it cannot be temporarily true. So actually the 0 here is irrelevant. However, when the agent moves and moves without going through the lake, makes the formula temporarily false. And so it gets assigned -1. And this keeps happening for each move of this kind till the agent gets to the delivery point, at which point makes the formula permanently true, and so gets assigned +1. Now let's consider another run in which the agent goes directly into the lake. In this case, the agent makes the formula permanently false, and so it gets assigned -10. If it now keeps going through the lake, still gets assigned -10, and also if it goes out of the lake, keeps getting assigned -10, because now the formula is permanently false, and there's nothing it can do to make it true. And this is true also in the final step where it gets to the delivery point. In the paper, we show how to realize monitoring rewards via transducers. So let's consider a monitoring reward where, as I said before, the reward condition is expressed, phi is expressed in LTLF or LDLF. This monitoring reward can be equivalently captured by temporal specifications with conditions expressed in LDLF. What does it mean that can be captured? It means that we can, for instance, the first specification checks whether the phi r, the condition phi r is true exactly when the original condition phi is temporarily true. In this case, we assign R. And similarly with phi c, phi s, and phi f. The reward condition can be, these reward conditions can be translated into DFA, so into acceptors. And now what we can do, we can assign the corresponding values when the corresponding automaton is in the final state. In the paper, we went further and we gave a more refined construction. This construction makes use of reward transducers. So transducers, they map partial traces to rewards. We have two kinds. We have more machines and mini machines. In the case of more machines, we have a finite set of states, an input alphabet consisting of pairs, state and action, state of the MDP and an action, and a finite set of rewards, the rewards we want to issue, an initial state, a deterministic transition function, and an output function that maps each state of the machine to a reward. In the case of mini machines, things are similar, except for the fact that the output function depends also on the current input symbol. So in the current state coming from the NDP and action coming from the agent. In the rest of the talk, I will focus on more machines because our constructions are not really different in the two cases. And so I'll just focus on more machines. Going back to our construction, here we have shown that a monitoring reward can be captured by these four acceptors. However, instead of having acceptors checking the condition and then issuing the corresponding value, RC, S, or F, we can include these values directly in the reward in the machine and so obtain a reward transducer. Then the interesting thing is that these four transducers are almost identical except for their output function. So they can be easily combined by taking the components of any of them and then computing a new output function by taking the sum of the initial output functions. This way we have obtained a reward transducer that implements the initial monitoring reward. Going back to the case of the mail delivery agent and of its monitoring reward, we have that this monitoring reward can be captured by a transducer that outputs -1 whenever the formula is temporarily true. Whenever the formula is temporarily false. A transducer that outputs +1 whenever the formula is permanently true, and a transducer that outputs -10 whenever the formula is permanently false. You can also consider the transducer for the temporarily true case, although it doesn't output anything because this formula is never temporarily true. These for transducers can be easily combined into another transducer, which has the same size of the initial one and an output function computed by taking the sum of the other output functions. We decided to work with reward transducers that directly represent reward functions. An alternative is to work with acceptors, in which case each acceptor tells us when a reward condition is satisfied, and then we issue the corresponding reward. However, if you're not interested in the source of rewards, reward transducers are a better formalism than acceptors. In fact, we can combine multiple transducers into one transducer easily by taking the sum, for example. And in some cases, like in the case of monitoring rewards, we can save states compared to keeping around different acceptors. As it was true for decision processes with rewards specified through temporal specification, it is also true for decision processes with rewards specified as monitoring rewards that we can obtain an equivalent Markov decision process. In our construction, instead of going through a deterministic finite automaton, now we go through a transducer to compute an extended state space and corresponding Markovian transition function and reward function. To conclude, I have presented monitoring rewards, which are a formalism that improves on existing temporal logic specifications for rewards. In particular, it allows for better control over reward assignment at no additional cost, in the sense that there's no overhead introduced there are no additional states introduced in the final Markov decision process. In the future, we would like to look at reinforcement learning, in the sense that we would like the agent to be able to learn non-Markovian rewards without the help of the extended state space. And we'd also like to look at reinforcement learning in the case in which both rewards and transitions are non-Markovian. Thank you.